Ladies and gentlemen, I give you the Calvin cycle. Let's begin by drawing our thylakoid disc, because this is all going to happen in the stroma, and that'll orient us. So there's our thylakoid disc, the stroma is out there, and we start down here in the bottom left-hand corner with carbon dioxide. Carbon dioxide is going to bond with a C5 molecule. Now this C5 molecule has hydrogens and oxygens bonded to it, but we don't care about those hydrogen oxygens right now. We're just going to count the carbons. So there's our C6 molecule. That C6 molecule immediately splits into two identical C3 molecules. Do you see how 2 times 3 equals 6? Now that C3 molecule, or sorry, both of those C3 molecules will go through a different reaction. And they're going to turn into a different C3 molecule. Sorry, two different C3 molecules. So I'll put a little asterisk in there. Now they're going to need some energy to do this, so you guessed it, Jimmy, they're going to get it from ATP. ATP is going to break down to make ADP and deliver energy so that that reaction can happen. Not only is ATP giving energy, he's also giving the phosphates. So if our math is at all awake, we're going to need two ATPs since there are two C3s. Now, that 2C3 with a P, he needs some electrons. Where do you think he's going to get the electrons? From the native? That's right, Jimmy. You're so smart. Now, that native is going to break down, give electrons to the 2C3 with a P. He's going to make NADP plus. See, he's lost an electron. And a hydrogen ion. He too has lost an electron. We're going to make a different C3, two different C3 with P's. And he's different than the other one, so instead of an asterisk, let's give him a smiley face. They differ in that they have hydrogens and oxygens bonded in different places. A lot like we did think about glucose and fructose being differently organized, differently shaped. Now that 2C3 of the P is going to lose a carbon, and that carbon is going to be used for glucose. So we're just going to save it for now, because glucose got a heck of a lot more than just carbons, a carbon. And when those 2C3 with a P molecules lose a carbon, they only have 5 carbons left, so they're going to make a C5 molecule. That C5 molecule is going to go through several reactions and return at the beginning. The same C5 molecule that started the whole thing. And this, my friends, is called the Calvin cycle. But where did the ATP and native come? Jimmy, I'm going to get to that. But first, we have to realize that this cycle has to happen 6 times. Why do you think it has to happen 6 times? Who knows how many carbons are in glucose? Anything, Jimmy? Well, I'll tell you, there are 6 carbons in glucose. That's why. Now, the ATP and the native, they come from the light reactions. And you can see that we get the ADP that we need in the light reactions from the Calvin cycle, and the NAD pluses and H pluses from the Calvin cycle. So they're in their own little cycles going back and forth. So here I'm going to quickly draw the light reactions just so we can ultimately see how the light reactions make the ATP and native, and then they're used in the Calvin cycle, and then the ADP and the NADP plus are brought back and used in the light reactions. See right there, there's the ATP. Of course, we need some free phosphates because we gave them away to the asterisk C3. But we finish everything out, and that's photosynthesis. And when we look at the general reaction, sun's energy, CO2, and H2O, that makes glucose and oxygen. And we can see all of those things where they are inputted, where they come out, etc.